Hello everyone, welcome back to PC 301 workshop, and today is the third day of our workshop. We start with the first talk of the day, and we have with us Roohani Sharma from Max Planck Institute for Informatics, and this is her second talk at the workshop. So thank you so much, Roohani. Over to you now.
Thank you. We continue from where we left yesterday, though the parts that we'll discuss today are independent of what we discussed yesterday. But what's important for us is to remember what we are doing, and what we are doing is kernelization. And this is like one slide summary of what is kernelization. We are trying to design efficient pre-processing algorithms, like polynomial time algorithms, that takes an instance of a parameterized problem and returns an equivalent instance of a parameterized problem of the same parameterized problem where the instance size is bounded by the function of the parameter. And typically we are, so if a problem admits such an algorithm, we say that the problem admits a kernel of size gk, where gk is the size of the reduced instance. And typically we're interested in designing kernels where the function gk is a polynomial function of k, or in other words, we're interested in designing polynomial kernels. So just briefly where we left yesterday. So yesterday we saw a few examples of problems, and we designed kernels for them. And for some of them, we designed kernels using simple combinatorial insights about the problems. For the others, we of course needed insights about the problem themselves, but we also needed some nice tools like the sunflower lemma tool from the combinatorics world to actually get our kernelization results. And I left at one question yesterday about the vertex cover problem. We saw a kernel of vertex cover which has order k square vertices and order k square edges. And I also said, and Peter in the last talk yesterday reiterated that vertex cover cannot admit kernel where it cannot be compressed to an instance where the number of bits in the instances bit size is order k power 2 minus epsilon. So you cannot improve the quadratic dependence as far as shrinking of the bit size is concerned. But this still does not refute getting a kernel where the number of vertices is order k, because even if the number of vertices is order k, the number of edges could very well be k square, and we still don't refute any of the lower bounds there. So we will touch upon this aspect of the vertex cover today. And in particular, the goal for today is the following. So today, the aim of this talk is to get ourselves introduced with 3 more tools which are widely used to design kernelization algorithms. And those 3 tools are the ground decompositions, and then expansion lemma, which in some sense is a generalization of the ground decomposition. And then we'll also see how we can design kernels using linear programming, linear programs. In particular, we'll see how linear programs can guide us to design reduction rules that helps us get polynomial kernels. So the broad theme will be to understand what these tools are, and in particular, we'll also be interested in showing, using these techniques, the following 2 results. The first one is, as promised, we'll see a linear vertex kernel for vertex cover, in particular a kernel with at most 3k vertices using ground decompositions. And later we'll improve the size of this kernel to 2k using linear programming. So again, the goal is to understand these 3 techniques, to focus on these 2 results. And on the course of understanding these techniques, we'll of course touch upon a few other problems to illustrate these techniques. So we also have a few other problems apart from what is already listed here. So let's start with the first technique of the day, which is the ground decompositions. And instead of telling you what ground decompositions are, what grounds are, let us start from the very basics so that we get a hack of where this concept is coming from. And to get that starting point, let's actually start with this kernel, with this problem, the problem of designing an alternate kernel for vertex cover. And let's see what more rules can we have for vertex cover, and then we'll see if we can try to generalize these rules, and those rules will lead us to our final name. So let's start with the vertex cover problem again. And in case you've forgotten what the vertex cover problem is, here's the definition for you. So you have a graph G, you have an integer k, and you want to delete at most k vertices from the graph such that the resulting graph is an independent set. Or in other words, if you look at any edge in the graph UV, at least one of its endpoints should be contained in the solution set. So yesterday we saw a quadratic vertex kernel for the problem by designing two rules. The first one was, we said we could easily delete isolated vertices. And the second one said that if there is a vertex of high degree, then just be greedy and pick that vertex in the solution. And by high degree, we meant degree k plus 1. And we showed that this rule is safe. It's fine to be greedy and delete or pick high degree vertices in the solution. So today let's start with a different rule, which is quite simple, and let's see where it gets us. So consider the following rule. This is called the degree 1 rule. So let's say there is a vertex, a yellow vertex V, and it has degree 1 in the graph, and let the red vertex U be its unique parent. Now, what can be said about these two vertices, red and yellow? So yellow vertex has only one edge incident on it. Now this one edge, the red yellow edge, has to be the vertex cover has to pick at least one of the endpoints of this edge. And now the observation is that we can always assign U to do the role of hitting this edge. So in this scenario, it's not difficult to see that we can always choose to pick U in the solution, drop the budget by 1, so we get this graph, and then after that V becomes isolated, and then we delete V2. And the reason we could just greedily choose U to do the task was because the vertex U, or the red vertex, was hitting at least as many edges as V, and probably maybe more. So U was doing at least as much task as we could do, and hence, in some sense, we can think of it as we delegated the its responsibility to cover the edge incident on it to the red vertex by saying that you can do at least as much as I can do, and someone needs to do the job, which is the job of killing this red yellow edge. So you go ahead and do it. So this is the principle. This is a very simple reduction rule, but I'm elaborating on what is the basic principle which makes it work, because we are going to generalize this principle. So I've just written down the basic essence of why this rule is safe. This rule is safe because what we are saying here is the yellow vertex is saying to the red vertex that you can do what I can do and probably more, and at least one of us needs to do the job. So you go ahead and do it. So with this essence, let me call this the delegation principle. So with this essence, or with this delegation principle, let's see how far can we stretch this degree 1 rule. Okay. So in particular, in this slide, let me try to construct some instances and see if we can apply this delegation rule to these instances and see where we can and where we can't. And based on our understanding of these instances, we'll try to develop a more general rule in the next slide. So now what are we gonna do? We'll have, in every instance that is gonna be there in the slide, the instance will have some yellow vertices and some red vertices. And what we need to decide now is that, can we say that all the yellow vertices can just freely delegate all their work to the red vertices, which means that we decide for sure that we are not going to pick any of the yellow vertices, and we'll pick all of the red vertices, because red vertices do as much job as yellow vertices, and picking up red vertices is not more expensive than picking up yellow vertices. So let's see if we can say these kind of things for the instances that I have in this slide. So look at the first slide. This is pretty much like the previous example. So you have a red vertex and you have a bunch of blue vertices. Here the bunch of yellow vertices. Here the yellow vertices can delegate their tasks to red, because if you look at the edges incident between the red and the yellow vertices, someone needs to kill these edges, and red vertex can kill all these edges. And uh, if you pick a yellow vertex, it can kill only one edge, whereas red ends up killing more than what a yellow vertex would do. So in this case, we can in fact greedily pick red in the solution and drop the budget by one, and then remove all yellow vertices because they become isolated in the graph. And similarly, we can apply this rule in combination also. Suppose we have a collection of red vertices which may or may not be connected by an edge, and then they have some bunch of yellow vertices hanging down them. In this example, again, we can choose to pick all the red vertices. Like the yellow vertices can delegate their job to the red vertices, and it is fine to greedily pick all the red vertices in the solution. Now, let's look at the next example. So the next example is a little different in the sense that the yellow, like in the earlier examples, the yellow vertices were very private to the red vertices, but now there are some red vertices, let's say, that share a yellow vertex. Can we still say that, okay, if you have such an instance, then just go ahead and pick all the red vertices in the solution? Can we say that? And I'll wait for an answer if someone has one to this. So the instance is like this. There are these two, so the instance is exactly this. There are these two red vertices and there are these yellow vertices, and then there are remaining vertices, and I don't care how those remaining vertices are connected. And I'm just looking at this local part of the graph, and in this particular instance, can I say that can I say that just go ahead and pick all the red vertices in the graph, all these red vertices into the solution? So no one? Okay, so Soban says yes. So Soban, can you unmute yourself and say why you say yes?
Because any cycle passing through the yellow vertex is mass passed through red vertices, right?
We're not talking about cycles. We're talking about the vertex cover problem.
Oh, sorry. So any edge which is adjacent to one yellow vertex is adjacent to those red vertices as well.
Okay, sure. So yes, we can do this, but I think this is not a complete explanation, and let's see why. So let me give you the next instance, and the next instance is this. In this instance, can you see the same? Can you delegate the job to red vertices and just delete all the red vertices in the graph? So note that what's happening here. So what's happening in the last example that is there on the slide is that there is only one yellow vertex, and of course the red vertices do the job of the yellow vertices. But now when we're doing this delegation from yellow to red, we are paying more. Right? So for example, maybe the solution actually picks this yellow vertex because it does not want to spend a budget of 2, whereas in this case it can spend a budget of 1 by picking this yellow vertex, and maybe the edges or incident on the red vertices are killed by some other vertices. Right? So it's not enough to just say that look at all the edges that are incident on the yellow vertices. If they are incident on the red vertices also, then the task can be delegated. The delegation should be such that the delegation should not be an expensive procedure. For example, in this example, it will be expensive if we delegate, right? So if I have to so the correct argument for the third instance would be the following. So note that I on purposely drew some extra vertices for each vertex of red. So each of these red vertices had an extra yellow vertex hanging out of it. And now note that now if you just focus on this one yellow vertex for this red edge and one yellow vertex for this red edge, we know for each of these two edges, for these two edges, one either a yellow or the corresponding red vertex has to do the job. And in this case, we can decide that the red vertices do the job. So because of these yellow edges, anyway, we can do the delegation. And it turns out that once we do this delegation, based on the fact that these red edges were seeing these yellow vertices, this delegation then helps to kill all the other edges incident on the yellow vertices also, because red edges were seeing lots of yellow vertices. So if this makes sense, like at least what I've said so far, please put a +1. Otherwise, please ask a doubt if you have any. Okay, good. So this is what we have. So now let's go to the next example, and let's see what you can say in this example. So in this example, none of the red vertices has a private hanging vertex from it. But can you still say something in this? Can you delegate the job of the yellow vertices to red vertices in this instance? Okay, so Shelly says yes. Can you unmute yourself and say why? Am I audible?
Yes.
Okay. So, or maybe I'll just give an answer. So even in this instance, we can do the delegation. And the reason we can do this is because of following. So note that it was not important that these yellow vertices were private to red vertices. What was important was the following. What is important is 2 points. First, whatever job yellow vertices can do, red can do. And that's true in this example. And secondly, the delegation should not be expensive, in the sense that if we plan to pick all the red vertices in the solution, there should be a reason why the solution should contain these many vertices, right? And in the last example that I've drawn, the reason that the solution must contain at least 2 vertices, should contain these 2 red vertices, is because if you look at a red vertex, you can assign one yellow vertex to each of them. It might not be private to it, but you can like uniquely assign, like for this red vertex, you can uniquely assign this yellow vertex to it. For this red vertex, you can uniquely assign this yellow vertex to it. And now just focus your attention on these 2 edges, this edge and this edge. Someone needs to take responsibility for these 2 edges. And now, if one of the yellow vertices was taking responsibility for one of these edges, then this yellow vertex can delegate its job to the red vertex. Or in other words, if there are 2 red vertices here, there were 2 jobs to be done, and both the jobs and probably more can be done by the red vertices, and hence we can still pick both the red vertices in the solution. So this can still be done. And here's my last example. So we have exactly the same structure now, but now the yellow vertices also share an edge between them. In this case, can we delegate the job of yellow vertices to red vertices? Actually, this case is pretty simple. The answer is simply no. And that's because when we are delegating the job of yellow vertices, when we delegate, meaning yellow vertices will never participate in solutions. But if yellow vertices do not participate in solutions, who is going to cover the edge incident between the yellow vertices, right? So the moral of this whole slide is the following. If you have a set of red vertices and if you have a set of yellow vertices, such that whatever edges can be hit by the yellow vertices, those edges can be hit by the red vertices also. Plus, there is some structure in the graph that tells us that the solution must pick at least number of red many vertices inside it, in those scenarios, you can actually delegate the whole of the job of the yellow vertices to the red vertices and end up picking up the red vertices. So let me now formalize what I just said. So so now I am partitioning my graph into 3 colored sets. One is the yellow set, which I have drawn in a crown. One is the red set, which I've drawn as a circle, and one is the rectangle set, which I've drawn as black. So the red set basically will correspond to the red vertices coming from the previous slide. Yellow set will correspond to the yellow vertices, and the black set corresponds to the other vertices in the graph. Now, the claim is the following. Suppose you can find a partition of the graph into 3 sets like this, such that, first of all, there is no edge between the yellow vertices. So that means the yellow vertices form an independent set. Also, there is no edge between the yellow vertices and the black vertices, which means that all the edges that are incident on yellow vertices are incident on the red vertices also. So in case you're looking for, if you pick the whole of red set, you know for a fact that you will kill all edges that yellow would kill. And now the third property is that, look, there is a matching saturating the red set into the yellow set. So there is a matching between the vertices of the red set and the yellow set, and this matching saturates the red set, meaning there is a matching with one edge incident on every vertex of red. So if you have such a matching, this matching says that, so this matching basically denotes the disjoint jobs that needs to be done. So for each of this edge, says that one job needs to be done, and each one of these jobs can be done by has to be done by a new vertex. So 2 different jobs corresponding to the matching cannot be done by one vertex. So a matching saturating the red set into the yellow set denotes that there are many disjoint jobs that need to be done. So if we pick up the whole red set, we need to pick up at least as many vertices as there are in red in this graph, which is induced by the yellow and red set. And because we know we need to pick as many vertices as red, now we know that if we pick red, we do the job because yellow was not doing anything more than what red was doing. So this is the structure that, so we can generalize the degree 1 reduction rule to this structure. And this structure has a name. In particular, the yellow part is called the crown, the red part is called the head, and the remaining part is called the body. And the properties of these sets are as I wrote here. So if the graph admits such a decomposition, then for the vertex cover problem, we can always choose to pick all the vertices of the head into the solution. We delete them. Once we delete them, the vertices of the crown becomes independent vertices, isolated vertices, because they didn't have edges between them. The only edges incident to them were with vertices of red, but we've already removed the vertices of red. So once we decide to choose that the vertices of red goes to the solution, we pick them into the solution, yellow becomes isolated, and then we delete those vertices and we get a reduction rule. So if we have such a structure, we can design a reduction rule by picking the head into the solution, and then because the crown becomes isolated set, we delete it too. So this rule is the one that we're gonna use for our vertex cover problem today. But now the problem is, yes, if we can find such a structure, yes, sure, we can apply the reduction rule. But how do you find such decompositions? And even more preliminary question is, why should these decompositions exist, or whether they should exist in the graph or not? And the next lemma answers the previous 2 questions in positive. It says that if you give me a graph which has no isolated vertices and you give me any integer k, then I'm guaranteed to output you one of the following. I'll either output you a crown decomposition of the graph, in which case for the vertex cover problem, you can apply the reduction rule, or I'll give you a matching of size at least k plus 1. Or if I'm not able to do any of the above, then I know for a fact that the number of vertices in the graph is bounded by at most 3k. So with this lemma in hand, now we have a 3k size vertex cover kernel, vertex kernel for the vertex cover problem, because we apply this rule. If we get a ground decomposition, we apply the reduction rule. If we get a matching of size at least k, then for the vertex cover problem, we can say no, because if every vertex cover of the graph has size, at least the matching size in the graph. So in this case, there is no vertex cover of size at most k, we can say no. And in the other case, we return a kernel with 3k vertices. And one good thing about this lemma is that this lemma is algorithmical. So one can find these things in polynomial time. So if we have this, we get a kernel for vertex cover. And now let's look at the proof of this. Let's see, why do we have this? Why do we say we have this? So for the proof of this, and in general, throughout the talk, we'll need 3 theorems from classical graph theory. And let me just state them here. Let's just refresh those theorems now. So the first one is the conics theorem, which says that in a bipartite graph, the size of the minimum vertex cover is equal to the size of the maximum matching. Then there is one that again says that if I have a bipartite graph with one side A and one side B, and I want to find a matching saturating the side A, then such a matching exists if and only if for every subset of X of A, the neighborhood of X in B is at least as big as the set itself. And then there is these are structural theorems, and then there is an algorithmic version of this theorem that given by Hopcroft and Karp, which says that given a bipartite graph, one can in polynomial time actually find a maximum matching and a minimum vertex cover. And it can also find if there is a matching saturating the set A. And if it is not able to find a matching, then it will actually return a witness. So Hall's theorem says that if there is no matching, then there exists an X such that neighborhood of X is strictly less than the size of X. So this algorithm says that if it's not able to find a matching, it will give you a witness, and that witness comes in the form of a set X, whose neighborhood is strictly smaller than the size of the set itself. And this witness is inclusion-wise minimal. That means for every subset of this set X, that subset satisfies the Hall's inequality. But if you include one more vertex in the subset and form X, then X does not. So this is what we have, and this is what we'll be using. So let's come, and we'll call this witness as the Hall's set. So let's proceed to the proof of the ground decomposition lemma. So for the proof of the ground decomposition lemma, so we need to find some independent set that will serve as our crown, and then we need to find a set that will serve as our head, and so on. And one starting point towards for it could be the following. So we need to get hold of some independent set where we can try to find our crown first. And for that, let us do the following. So let us find some approximate vertex cover in the graph. So, and that can be done simply by finding a maximum matching in a graph, and then if its size is greater than k+1, then you just return the matching, because the ground decomposition lemma allows you to return a matching of size k+1. Otherwise, you get a vertex cover of size at most 2k in the graph. So let this red set correspond to this vertex cover, and I'm denoting that set by M. And now, if this is the vertex cover in the graph, if you look at the remaining graph, which I've denoted by yellow right now, that will be an independent set. So now our goal will be to find some crown sitting inside the yellow set and some head sitting inside the red set. And let's proceed. So to do that, let's now do the following. Note that if the size of the independent set is at most k, then we conclude that the total number of vertices in the graph itself was at most 3k. Otherwise, we know that the size of the independent set is at least k+1 or strictly greater than k. So now we do the following. Now we just look at the sets M and I and find a maximum matching between these two sets. So just look at the sets AM and AI and find if there is a matching with endpoints which are across the sets. And this matching can be found using the Hopcroft-Karp algorithm. And again, if there's a matching of size k+1, you return that matching. Otherwise, we get a matching of size at most k, and this is the blue matching that I've drawn here. And Konig's theorem says that if there is a matching of size at most k, then there is a vertex cover of the red-yellow bipartite graph. So if you just forget about the edges inside the red part for a moment and just focus on the edges going across the paths, then these edges can be covered by a vertex cover of size at most k by Konig's theorem. Now let us look at that vertex cover. So this vertex cover will precisely pick exactly one endpoint from this matching, because every vertex cover has to pick at least one, and since the size of the vertex cover is equal to the size of the maximum matching, it will pick exactly one endpoint. And note that since the size of I is strictly greater than k and the size of the vertex cover is at most k, all the vertices of the vertex cover are not coming from the yellow part. So there exists at least one vertex in the red part. Now we get hold of those vertices of the vertex cover in the red part. These are these black vertices. And now my claim is this will be the head set of my crown decomposition. And if this is the head set, I look at all the neighbors of this head set in the yellow part, which are, so for example, if you look at this black vertex, this is a neighbor of this dark red vertex, which I have assigned as head, but this is a part of the vertex cover, so I'll not pick this into my crown, but I'll pick every other neighbor of this set into my crown. And my claim is then these set of vertices form the crown. And let's see why. So this is definitely an independent set. And we need to show that the only edges incident on these vertices in the crown are the edges of the dark red set, which is the head. And that's indeed the case, because if there is a vertex, if there is an edge incident on this crown and the other endpoint lies outside the vertex cover vertices from the red part, then note that since the crown did not contain any of the vertex cover vertices, this edge is not covered by any of these black vertex cover vertices that I've drawn, which contradicts that the black vertices formed the vertex cover of the bipartite graph. So these edges are not present. So this independent set actually is the crown in the sense that this sees only vertices in the head. And another thing that we need to prove for a crown is that there's a matching saturating the head, and that is indeed the case because of these blue edges. So we have actually found a crown decomposition of this graph, right? So this finishes the proof of the crown decomposition. And using this, we have also given a 3K vertex kernel for vertex cover. So now what I wanted to point out next was the following. So, but I'll skip this part, but let me still say it, that like a lot of problem admits these crown reduction rules. So for a lot of problems, if you can actually find a crown decomposition, then you can actually try to delete the head and pick the head in the solution the way we did for vertex cover and proceed with some reduction rules. But there's just a small caveat, because the way the crown decomposition lemma is designed, it does not necessarily guarantee you to output a crown decomposition, because sometimes it can output you a k+1 matching of the graph. And in which case, for a problem like vertex cover, we are still happy if we get a k+1 matching, because that helps us decide that the instances are no instance. But for many other problems, this information might not be very relevant. So, and for example, one of the problems is the long cycle problem that I wanted to discuss, but I'll pass this. But I wanted to say that for lots of problems, even if we can't use the crown decomposition lemma to find a crown decomposition, one can find crown decompositions in those instances by very basic means, and one can still exploit the structure of crowns without using the crown decomposition lemma and without getting the matching business in head. So this is one problem that exhibits that property, but I'll skip the proof of it and jump to the next tool, which is the expansion lemma. And as I said before, expansion lemma can be thought of as a generalization of the crown decomposition lemma. And the generalization is in the following sense. So the expansion lemma also gives us a similar decomposition like the crown decomposition gift, but it gave us something more. And something more was as follows. So the crown asks us to give a matching saturating the vertices of red, the vertices in the red set, the vertices in the head. But crown decomposition asks for something more. It asks for something called a Q matching or a Q expansion, and that is as follows. So it, like for example, so for example, in this example, we are wanting that every vertex of red has two distinct matched vertices in the crown part. And this is true for every vertex of red. So this vertex has two distinct neighbors in the crown. Then this vertex has two disjoint neighbors in the crown, disjoint from the neighbors of the previous red vertex, and so on. And we'll see where these kind of structures are useful, but let me just formally define what I just stated. So one can define a generalization of a matching, and this generalization is called a Q expansion. And let us just define it for bipartite graphs. So given a bipartite graph G and B, with bipartitions A and B, a set of edges M are said to form a Q expansion of A into B if M is actually a disjoint union of A many Q stars. So a Q star is a graph with one vertex called the center and Q leaves. So if M is a disjoint union of Q stars and there are A many Q stars, each has its center in A and the leaves of it lies in B. So here is a picture. So if you have a bipartite graph A and B, here is a 2 expansion of A into B, because for each vertex, so because I've given you disjoint stars, so they are 2 stars because they have 2 leaves each and they're all disjoint, and there is 1 star for each vertex of A. So for every vertex of A, there is a star that has it as its center. This is Q expansion, and clearly 1 expansion is just the matching problem. So let us see an equivalent decomposition lemma for Q expansion. So this is called the expansion lemma, and it goes as follows. It says that if you give it, and we define this lemma only for bipartite graphs, because in principle, when we apply this lemma, we end up applying it in some sort of an auxiliary bipartite graph. And so we define it only for bipartite graphs. So there is a bipartite graph G with partitions A and B, and you're given an integer Q, and you're given two things. One is that the number of vertices in B is at least Q times the number of vertices of A, and then there are no isolated vertices on B. Given these two things, the expansion lemma guarantees that you can always find a set H, which corresponds to the head, and a set in A, and a set C in B, which corresponds to the crown, such that there is a Q expansion from A, this should be from H to C, not A to B. So there is a Q expansion from the head to the crown, and the crown, if you look at the neighborhood of the crown vertices, they are all in the head. So the crown does not see anything outside the head. So note that because we're in a bipartite graph, such a set, this is exactly the crown decomposition with the property that now we have a Q expansion saturating the red set into the yellow set. So this is what we have, and I'll not go with the proof of it. The proof of it uses very similar arguments like the proof of Hall's theorem, which goes by induction on A. So I'll just skip the proof of it, but let's just try to see examples where this can be applied. So, and so let's look at an example problem for this, and the problem is called component order connectivity problem. So this is again one of the generalizations of the vertex covered problem. Let's see why. So in this, the input is a graph G, and you're given integers K and P, and the question is, can you is there a set of size? Is there a set of vertices of size at most K, such that when you delete those K vertices, every connected component of the resulting graph has at most P vertices? So note that in vertex cover, if you delete the vertex cover from the graph, every connected component, which is basically a singleton set, because what you have below is an independent set. So when P is equal to 1, this is in fact the vertex covered problem. And now we want to design a kernel for this problem using for higher values of p, and let's try to do this using expansion lemma. So let's proceed. Note that the problem can be stated in a different way also, and the way is as follows. So one can think of the solution set as hitting. This should be hitting. So any solution set will definitely hit a connected set of size at least p plus 1 in the graph. So what is a connected set? A connected set is a set of vertices in the graph that induce a connected graph. So if you look at any solution of this problem, the COC problem, then that solution has to intersect with a connected set, because if it does not intersect with a connected set, this connected set is going to go and sit in some connected component of the graph. And since this connected set is size p plus 1, you get a connected component of size at least plus 1 after the solution has been removed. And similarly, the other way around, like if the solution hits all connected sets of size at least p plus 1, then if you remove this such a solution, every connected component will have size at most p, because if not, then since every connected component is also a connected set, the solution must have hit this set. So this can also be looked at as a hitting problem where you're trying to hit large connected sets in the graph. So let's try to attack this problem, and let's start by finding some approximate solution to the problem. And this is again a typical step in designing kernels. So finding an approximate solution, or sometimes we also call it as a modulator, gives some structure of the graph, and then we exploit that structure to design kernelization, to design some reduction tools. So let's start by finding an approximate solution, and this is not very difficult to find. For example, one can greedily pick disjoint connected sets of size p plus 1 in the graph. So one can find a connected set of size p plus 1 in the graph by simply doing a BFS starting from any vertex, and do BFS as long until you have covered at least p plus 1 vertices. And when you cover p plus 1 vertices, those will form a connected set in the graph. So you just find a maximal collection of connected sets in the graph. If this collection has size k plus 1, then you know there is no k size solution, because every solution needs to hit one of these connected sets. And otherwise, let A be the union of the vertices in the sets of this collection, and A will have size p plus 1k, because every set in the collection has size p plus 1. The number of sets is at most k. And because C was a maximal collection of such connected sets, we know that every other connected set of size p plus 1 definitely intersects A. So A is in fact a solution of the problem, and it is some approximate solution. It has size at most p plus 1 times k. So let's start with A. We remove A from the graph, and what we get below are connected components of size at most p, because A was a solution of the graph. And now note that if the number of connected components of the graph is at most p times A minus 1, then we definitely get a kernel, because the number of components is bounded and the size of each component is bounded by p. So we get a kernel of size order p cube k. So the problem happens when there are lots of connected components, in which case we need to do something. So if the number of connected components is at least p times A, then we want to use p expansion lemma. So when I say p expansion lemma, meaning the q in the expansion lemma, I want to set it to p. And let's see, how do we use the expansion lemma? So we for the expansion lemma, we need to create a bipartite graph. Let's create a bipartite graph as follows. So there is a vertex there is the set A as one part of the bipartition, and then for every connected component below, let's create one vertex and put those vertices in the part B of the bipartition. So this is the bipartite graph, and the edges in this graph are such that if this vertex sees some vertex in this connected component, then I put an edge between this vertex and the corresponding vertex of the component. And now the expansion lemma says that if the size of B is at least P times A, then, and there are no isolated vertices in P, then you can actually find a P expansion from A to B, from some subset of A to some subset of P. And note that, so because the number of connected components is at least P times A, and if there was, let's say there was a component which didn't see any vertex up there, then we can have a simple reduction rule by, and we can simply delete such components from the graph, because these are actually isolated components in the original graph which have size at most p. So these components can be safely removed a priori. So every vertex here corresponding to a component sees some vertex here. So there are no isolated vertices in the set B that we have constructed. So we are ready to apply the Q expansion lemma. And so we apply the Q expansion lemma with Q equal to P, and we get the following. So we get a head set, which is the red set in A, and we get a crown set, which is the yellow set in B, with the property that for every vertex of the red set, there is a Q star into yellow, a P star into yellow, and the neighborhood of these yellow vertices is only inside these red vertices. So these yellow vertices don't see anything outside the red vertices. So this is what we get. And now let's see what we can do with this. So, and here, let me also point out why we needed a Q expansion and why simply a crown decomposition would not have worked. So crown decomposition would only have guaranteed you a matching saturating the red set, but what expansion is giving you is not just a matching, but something more. And the reason for having this something more is the following. Remember, we were talking about this delegation task for the vertex covered problem. And the tasks basically were represented by edges. So an edge represented a task, which could either be done by a yellow vertex of the red edge or the red vertex of that edge, right? And because the problem was vertex covered, we know that one of these vertices needs to hit it. So this is a task and one of these needs to do the task. So here, since the task is not about hitting edges, but the task is of hitting connected sets of size at least p plus 1. Now, if you look at this structure, if you look at this one red vertex together with the blue, together with the yellow vertices on which these blue star is incident, if you look at this part, note that this corresponds to a connected set of size at least p, because each of these are connected components, and we have at least p of them because we found a p expansion, and each of them see this red vertex. So together with this red vertex, this forms a connected set of size at least p plus 1, right? And this is true for every star in this Q expansion. Every star corresponds to a disjoint connected set of size p plus 1. Right? So now we can talk about delegation. So now there are red many stars in the Q expansion. So there are red many disjoint tasks that needs to be done. And now we want to again talk about some delegation properties. So we want to delegate the task of yellow vertices to red vertices. Now, how do we delegate the task? So note that why would a solution pick any of the yellow vertices? What would it achieve? So if you pick so a solution will pick a yellow vertex from the yellow set only if this yellow set can be extended to form some p plus 1 size connected set. But this p plus 1 size connected set has to pass via one of its neighbors of the yellow, because the yellow set in itself is very small, it has size at most p. So it has to pass via its neighbors, and all of its neighbors are in red set. So if we delete the whole of red set, there cannot be connected sets that can be formed with this yellow vertices. So in this case, again, we can do the delegation business. So there are red many disjoint connected sets that needs to be hit, and all of these connected sets that you can form amongst the vertices, red vertices and the yellow vertices, can be hit by the red vertices. So you go ahead and pick all the red vertices in the solution and kill those sets. So again, the delegation principle helps us here, but we needed this p expansion here. And so the reduction rule is just this. So if you find this set, you just pick the red vertices in the solution. You pick these red vertices in the solution, then these yellow components become isolated components. You delete them from the graph and proceed. And you keep doing that until you can't find a p expansion. And from And from the expansion lemma, if you can't find a P expansion, then the number of vertices or the number of connected components below will be at most P times A. And in this case, we get a kernel with order P square, P cube K vertices, because the number of, because the size of P is order Pk, the number of connected components will be bounded by P square K, and each component has size P. So here I would like to mention one thing, that this kernel bound of P cube K can be improved to P square K by using a weighted version of the expansion lemma. So I'll not prove or state what the weighted version is, but the idea is as follows. So note that here, when we were finding a P expansion, we were doing much more than what we were really expected to do. So all we wanted was that one star in the P expansion corresponds to at least one connected set of size P. And we like in the way worst case assume that maybe all the connected components below only have one vertex each. So I need at least P of them so that I can form a P plus one size connected set in the whole graph, right? But now let's say we have weights on these connected. So we have weights on, let's say, these connected components, and the weights corresponds to the number of vertices which are already there in the connected component. Then I can talk about a weighted star. So I say that a star has weight P if the following happens. So if you look at the star, look at the components on which the star is incident. If the sum total of all the vertices in this component is P, then I say that this star has a weight P. So now even if I have weighted stars, P weighted stars instead of P length stars, I can still apply this rule, because for each P weighted star, I'll get a disjoint connected set of size at least P plus one to hit, right? And because of this, one can improve, one can shunt out one of the P factors in the kernel size and actually get a better kernel. So I'm not going to the proof of it, but just wanted to mention that there are one can improve kernels by using variants of expansion lemma, and one of the variants is the weighted variant of the expansion lemma. So this is all that I wanted to say about the expansion lemma, and let's now move to the linear programming based kernels. So so now the goal is to design a kernel for vertex cover with 2k vertices. Now, so you have a vertex cover instance, and you're given a graph G. Let's say the vertices of the graph are V1 to Vn. So for those of you who don't know what is linear program, let me just briefly, quickly sketch it. So basically, it's a program which constitutes of variables, some variables, and then there is a function that you want to there's a function defined over the set of these variables that you want to either minimize or maximize, and this minimization or maximization should happen under some constraints on the variables. And we say that the program is a linear program if all these constraints and the optimization function can be written as a linear function of the variables. So these are what linear programs are. Now let us try to write a linear program for vertex cover, and let's see how far we get. So let's say let's say the vertices of the given instance are V1 to Vn. Now for each vertex, let's create a variable. Each vertex Vi, let's create a variable xi, and now let us write a vertex cover, a linear program for vertex cover as follows. So there are variables xi for each vertex Vi. And now the constraints are as follows. You want to say that if there is an edge between two vertices, then the variables should get values such that the end for these two vertices, their values should add up to at least 1. This is the constraint. And for this, this is not exactly a linear program, but let me still write it. So, and now I ask that each of these variables can take values only from the set 0 or 1. And now I try to minimize this function, which is the summation of all the values xi. Note that this exactly represents a vertex cover problem, because look at the variables that get vertex 1. If you pick those vertices in the vertex cover, then the vertices corresponding to those variables as vertex, they will form a vertex cover, because for every edge, at least one of the vertices will be 1. And we have taken all the vertices which got value 1 into the vertex cover. And this, in fact, will be a minimum vertex cover, because you are trying to minimize the summation of xi's, right? So this program actually correctly captures the vertex cover problem. But as I said before, this is not exactly a linear program, because one of these constraints here, the last constraint, is not exactly a linear constraint. It's an integer constraint, because it asks that the value of the variables should come from some integer set 0, 1. So this is the ILP for vertex cover, and we know that ILP solving is NP complete. In fact, what we just did was give a reduction from vertex cover to this ILP. So since vertex cover is NP complete, this solving this ILP is NP complete. But what's interesting about linear programs is that if I just relax the integer condition as follows. So instead of asking for values, but in the set 0 or 1, I asked for values that can take any values in the range 0 and 1, not necessarily integers, but it can take any values. Then this becomes a linear program, and such a program can be such a program can be run in polynomial time. Linear programming is in P time. So we can solve this program in polynomial time and get a solution for this. And in what follows, I'll call this summation value as the opt LP value in the linear program, and I'll call the summation values in the ILP as the opt ILP value. It's not difficult to see that the opt LP value is at most the opt ILP value, because any solution of the ILP is also solution for the LP. So this is the vertex cover LP that we wrote. Now, what a kernelization algorithm does is the following. It takes this program and runs this program and finds an optimal values of xi's that satisfies these constraints and minimizes this function. And based on these values xi's, which the program returns, we are going to design some reduction rules, and let's see what they are. So let's begin by first partitioning the vertex set based on the values that the variables for those vertices have gotten. So we'll partition the vertex set into 3 sets: set V strictly less than half, set V equal to half, and set V strictly greater than half. So the set V strictly less than half contains all those vertices whose corresponding variables have been assigned value strictly less than half by the LP program. Similarly, we have the set equal to half, and we have a set strictly greater than half. Now we have these sets, and now let us see what is the kind of structure that we can infer about these sets given the LP values, given that we know what kind of LP values do the vertices of these sets take. So these are the 3 sets that we had. So now note that if you look at any 2 vertices of this set, the yellow set, which is the V at strictly less than half set, no 2 vertices can share an edge, because both these vertices got LP values less than half, less than half. If they shared an edge, then the edge constraint corresponding to this edge would not have been satisfied, because the values don't add up to at least 1, because both of them are strictly less than 1. So they don't have edges, so which means this is an independent set. The yellow set is an independent set. So similarly, we can say that there are no edges of this form from V strictly less than half to V equal to half, again, because if you add up the LP values of the endpoints of this edge, it will add up to strictly less than 1, because this is exactly half and this is strictly less than half. So you don't have these edges. And now it is starting to look something like a crown decomposition that we already saw. And in fact, we can show that this is in fact a crown decomposition of the graph. And to prove that, if I show that there is a matching saturating the red set into the yellow set, or the vertices V strictly greater than half set to V strictly less than half set, if I say that, if I show that there's a matching saturating this red set, then this 3 sets will actually form a crown decomposition. And then we know we can design reduction rules. In particular, we can remove the red set and pick it in the solution and then delete the yellow vertices. But and for that, we need to prove that there is a matching saturating the red set, and let's see that. For the sake of contradiction, suppose there is no matching saturating the red set into the yellow set, then by Hall's theorem and by Hopcroft and Karp's algorithm, we can find a Hall set. So Hall set will be a set of vertices, set of red vertices, whose neighborhood in the yellow set is smaller than the set itself. So the yellow set is the neighborhood of the red set, and it is smaller than the red set, strictly smaller than the red set itself. And now if we find such a set, what we're going to do is we're going to tweak the LP values that the LP program had assigned, and we'll tweak it such that the new values are also valid LP values in the sense that they satisfy all the edge constraints, and we'll show that this new LP values give a lower value for the optimization function, thereby contradicting the optimality of the LP solution. So we want to go towards a contradiction by tweaking the LP values of some vertices here. And in particular, we'll tweak the LP values of the vertices of this red set and the vertices of this yellow set, and we'll tweak it like this. So we'll choose an epsilon, which is small enough, and I'll tell you what that epsilon is. And we'll decrease the LP values of all these vertices in the red set by epsilon amount. And I'll do so, but I'll still the epsilon will be so small that even after this drop, these vertices still remain in this set. So the LP values, the new LP values are still strictly greater than half. I'll do that. And then I'll go to the yellow set and I'll increment their LP values by at least epsilon, again ensuring that these increments still don't overshoot the strictly less than half condition for these vertices. We'll do that. And now I'll show two things, that these tweaked values also satisfy all the edge constraints. And then if I show you this, then note that now if I look at these new LP values, they give a smaller optimal solution to the minimization function, because from all the LP values, I have deleted epsilon from the LP values of the red set. I've deleted epsilon quantities from each of these sets, and I have added epsilon quantities for each of the yellow set, but the elements in the yellow set were smaller. So if I do this tweak, I definitely end up with a smaller optimal value, but I just need to show that this tweaking still satisfies all the edge constraints. And to see that, note that if I increase the LP value of certain variables, it's not going to contradict the edge constraints, because the edge constraints just say that the sum of the two endpoints of the edges should be at least 1. So increasing an NP value will not change those constraints. So we just need to be concerned about these vertices. But now for these vertices, note that look at the edges that are inside these vertices. They will still be those constraints will still be satisfied, because after tweaking, I'll still ensure that those vertices are the LP values are strictly greater than half. So so if I add up the new LP values, they'll still, for an edge inside it, it will still be strictly greater than 1. Similarly, we can talk about the edges that are across the red and the black set. Even after this decrease, because I have ensured that the decrease is small enough that the vertex still has LP values strictly greater than half, then for these kind of edges also, those constraints are satisfied. So the only edges for which the constraints might not be satisfied now are the edges that goes between the yellow and the red set, because now I might have decreased the LP values of these edges, and these may not be compensated, and we need to say that they have to be compensated by the endpoints in the yellow set. And that indeed happens, because if you look at any edge whose one endpoint is in the yellow set and one endpoint is in the red set, for each such edge, I have decreased an LP value of one endpoint by minus epsilon and increased the LP value of the other endpoint by plus epsilon, and thereby the total sum of the LP values stays the same. So those edge constraints are also satisfied. So if I can do this tweak where I ensure that after this tweak, the vertices remain in these sets, I'm happy, and I get a contradiction if I don't find a matching saturating the set, red set. And now it's not difficult to see that if you choose epsilon like this, you actually ensure that all the vertices in the red set remain in the red set, and all the vertices in the yellow set remain in the yellow set. And this is for the this is the proof. So what we have shown is that if there is no matching, then we get a contradiction. If there is no matching saturating the red set, so there's a contradiction. So what we have really is there is a matching saturating the red set, and we have all the other properties of the crown decomposition. So basically these three sets form a crown decomposition. And now, since we've already discussed that in a crown decomposition, we can safely pick these vertices in the solution. We pick these vertices in the solution, and there is a reduction rule. So this set of reduction rules, this kind of a crown decomposition was given by Nemhauser and Trotter. And because of this, because of them, we can get a crown decomposition like this and then apply this reduction rule. And now note that when is it that we can't apply a reduction rule? We can't apply a reduction rule when all the vertices in the LP, all the vertices get LP values exactly half. So when we don't have any of the red and the yellow sets, that's when there is a dead end. But then that's not a difficult thing, because when we reach this situation, note that in that scenario, the optimum LP value, which is the summation of x size, it will be exactly equal to n by 2, because each vertex takes value 1 by 2. And now since we know that LP opt LP is at most opt ILP, and opt ILP is actually the optimum vertex covered in the original graph. And since we're looking for a k size vertex cover, so k should be at least the optimal vertex cover, we get, so using this fact that k is at least n by 2, we conclude that when this happens, when all LP values are exactly equal to half, the number of vertices in the graph is actually just 2k. And hence we get a 2k size kernel for the problem. So this is all that I wanted to say about the technical results. So let me just go to the summary. So we discussed these three techniques. We discussed, basically we discussed these two results. I couldn't do the third result here. But in case someone wants to follow up on the kind of things that we have done, I have some pointers in green boxes that you might be interested in looking at. Yeah. So basically we saw this, and then for expansion lemma, we saw an application of the expansion lemma for COC problem. We saw that using weighted versions of the expansion lemma, you can actually improve the kernel sizes. And then this expansion lemma, which we didn't see, and if someone wants to follow up, it's a nice problem to follow up. We saw the feedback vertex set problem in one of the lectures earlier. And using an expansion lemma, we can get a ordered quadratic kernel for the problem. And we can get polynomial kernel for the feedback vertex set problem using other methods also. But the nice thing about the expansion lemma is that it gives a quadratic kernel, and this kernel is essentially tight, at least bitwise, size-wise. So there is this kernel. And then we saw for linear programming based kernels, we saw a vertex covered kernel with size with 2k vertices. And now a natural question here is we use crown decomposition to get 3k vertices, and now we use LP to get 2k vertices. What about, can we get 1.9k vertices or 1.5k vertices and so on? It turns out no, there are negative results. Under the unique case conjecture, we cannot expect that vertex covered kernel. We can get a vertex covered kernel with 2 minus epsilon k vertices. So what we saw here is essentially tight. And again, another thing, if someone wants to follow up, is like we saw a COC kernel. We hinted that we can get a COC kernel of size p square, order p square k using weighted expansion lemma. But again, it can be improved if one takes the linear programming route, and one can, if someone wants to follow up, they can see how one can design a better kernel for COC using linear programming. And I think I'll just stop here.